If what is happening to the North Atlantic Ocean right now has you paying attention the way it has me, hit like and subscribe to Signal Watch, because this is a story that is going to develop over years, and you are not going to hear most of it anywhere else. Drop a comment below. Tell me where you're watching from, what time it is there, and this. Do you eat seafood? Do you live anywhere near a coast? Because the answer shapes everything about how personally this story lands. And if you know someone who thinks the ocean is stable, who thinks what we're seeing is just weather, share this video with them. Not as a warning, as evidence. You are why we can keep doing this work. Thank you. Here's what this investigation covers. A number, a statistical probability, that peer-reviewed science published in Nature describes as effectively impossible, that happened anyway, and that the world has not yet absorbed the implications of. The specific atmospheric mechanism that triggered the most anomalous ocean warming event in the recorded history of the North Atlantic. The ecological cascade that is already underway beneath the surface, in the coral, in the plankton, in the fish populations that billions of people depend on for protein, and why the damage compounds each year that the anomaly persists. The atmospheric physics by which a superheated North Atlantic changes the weather system of the entire planet, not just locally but globally, by disrupting the circulation patterns that regulate rainfall, temperature, and hurricane intensity across the northern hemisphere. And what three distinct interpretations of where this goes from here tell us about the range of futures that the monitoring data currently supports. Now, let's get into it.
In April of 2023, something happened to the global ocean that peer-reviewed science published a full 2 years later, in April of 2025, in the journal Nature, would describe as a 1 in 512-year event. That return period, 512 years, is not a rough estimate. It is the central estimate from an analysis conducted by a team of climate scientists who built synthetic time series of 100 million years using autoregressive models calibrated to the observed statistical properties of the ocean temperature record. They ran 270 simulations from a wide range of fully coupled climate models. Their question was specific. How likely is it, given the long-term warming trend in the world's oceans, that global sea surface temperatures would break the previous record by at least 0.25 degrees Celsius? The margin by which they broke it in 2023 and 2024, 1 in 512 years. The 95% confidence interval runs from 1 in 205 years to 1 in 1,185 years. Even the optimistic end of that interval describes something that should happen, on average, twice in the entire span of recorded human civilization. And the North Atlantic's contribution to this global anomaly was even more extreme than the global average. The North Atlantic sea surface temperatures in 2023 and 2024 surpassed their previous record by 0.42 degrees Celsius, 0.17 degrees Celsius, more than the margin by which global sea surface temperatures had surpassed their record in the same year. The North Atlantic was not just part of this anomaly, it was leading it, driving it. The epicenter of what would become the most extraordinary ocean temperature departure ever measured. On July 31, 2023, global average sea surface temperatures reached 20.96 degrees Celsius, barely above the previous record of 20.95 degrees, set in March of 2016. But that global number concealed a regional signal that was far more extreme. In the northeastern Atlantic during July 2023, daily temperature anomalies, the departure from the average for that date, reached 6 to 8 degrees Celsius or more in some areas, according to the Copernicus Climate Change Service. The average anomaly for July 2023 as a whole reached 4 to 5 degrees Celsius across parts of the North Atlantic, not 0.6 of a degree, not 1.2 degrees. 4 to 5 degrees in the monthly average, implying daily peaks in some locations that exceeded that average substantially. To put 4 to 5 degrees of anomaly in context, climate scientists use the term unprecedented carefully and technically, reserving it for deviations from historical baselines that genuinely have no prior analog in the measurement record. The Copernicus Climate Change Service, the European Union's official climate monitoring system, operated by the European Centre for Medium-Range Weather Forecasts on behalf of the European Commission, used the word uncharted territory in its June 2023 bulletin to describe what was happening in the North Atlantic. Not elevated, not exceptional, uncharted. And when the paper in Nature used the phrase practically impossible to describe what would have happened in a world without human-caused climate change, without the warming that elevated the baseline from which these anomalies depart, it was making a precise scientific statement, not a rhetorical one. The 2023 event would have been impossible in intensity without anthropogenically driven climate change, according to the analysis published in Communications, Earth and Environment in April 2025 by Ginaldo Casu, Saleh, and Linné. Not less likely. Impossible. The scale of what happened to the North Atlantic in 2023 deserves to be held in the mind before we examine its causes or its consequences. Because the impulse, the very human impulse, is to slot this number into the category of alarming weather event that has since passed. The North Atlantic was hot. Now it is less hot. On to the next story. That is not what the monitoring data shows, and what it actually shows is the subject of this investigation. But before we can understand what the monitoring data shows, we need to understand one more dimension of that July 2023 temperature map. The Copernicus Climate Change Service data documented that anomalies in the northeastern Atlantic that month averaged 4 to 5 degrees Celsius across the monthly mean. But satellite-derived sea surface temperature maps from individual days, the daily snapshots rather than the monthly averages, showed localized anomalies exceeding 6 to 8 degrees Celsius in specific regions. 6 to 8 degrees above average. To give that number meaning, the entire difference in global average surface temperature between the peak of the last ice age and the current pre-industrial baseline is approximately 6 degrees Celsius. The ocean surface in parts of the North Atlantic in July 2023 was warmer relative to its recent baseline by the same margin that separates the modern climate from an ice age, not over tens of thousands of years of gradual change, but compared to the average of the previous 30 years. That is not a weather anomaly in the ordinary sense of the term. It is a signal from a system operating in territory it has never previously inhabited. The academic literature on the causes of the 2023 North Atlantic marine heat wave has produced a series of peer-reviewed papers that identify a web of contributing factors, and that are unusually explicit about the role of human activity in making the event possible. The primary driver, identified by Matthew England at the University of New South Wales and colleagues in a Nature paper published in June 2025, was not what many expected. It was not principally a surge of warm water from ocean currents, it was atmospheric. Specifically, anomalously weak winds over the North Atlantic, persisting for weeks, that allowed the ocean's surface mixed layer to become unusually shallow. Here is why that matters. The ocean surface is constantly exchanging heat with the atmosphere. Wind drives mixing. It churns the ocean surface layer, bringing cooler water up from depth and mixing the heated surface water downward, distributing the energy from solar radiation through a deeper layer. When winds are strong, the mixed layer is deep, perhaps 50 to 100 meters, and the heat absorbed at the surface is spread through a large volume of water, so the surface temperature rise per unit of solar energy input is modest. When winds are weak, the mixed layer shallows dramatically, sometimes to 10 or 20 meters. The same amount of solar energy is concentrated into a fraction of the water volume. The surface temperature rises far more rapidly. In the spring and summer of 2023, an anomalous atmospheric circulation pattern produced substantially below average wind speeds across large portions of the North Atlantic. The mixed layer shoaled, became abnormally shallow, creating a razor-thin surface layer that superheated rapidly under the strong solar radiation of the Northern Hemisphere summer. England and colleagues quantified this. The warming was primarily driven by air-sea heat fluxes acting on an extremely shallow surface mixed layer rather than by anomalous ocean heat transport from currents. The anomalous clear skies that accompanied the low wind regime added an additional, smaller contribution. Less cloud cover meant more solar radiation reaching the ocean surface. The result was a near basin-wide anomaly that spread across virtually all regions of the North Atlantic, including the subpolar ocean where a multi-decade cooling trend driven by the slowdown of the Atlantic meridional overturning circulation had previously prevailed. The anomalous warming not only reversed that cooling trend locally, but exceeded it by a large margin. Then there is the shipping regulation factor, one of the more counterintuitive and genuinely uncomfortable findings to have emerged from the literature on the 2023 event. In January 2020, the International Maritime Organization implemented new regulations requiring roughly an 80% reduction in the sulfur content of shipping fuel used globally. The stated purpose was environmental and public health. Sulfur dioxide emissions from ships cause acid rain, contribute to ocean acidification, and produce air pollution around ports. The regulations achieved their intended goal. Sulfur dioxide emissions from the global shipping fleet dropped dramatically. But sulfur dioxide, despite being a pollutant, was also doing something that climate scientists had long known about but not fully quantified in operational terms. It was cooling the North Atlantic. Sulfate aerosols, particles formed when sulfur dioxide reacts with the atmosphere, serve as cloud condensation nuclei. They seed the formation of clouds, and the clouds they seed are brighter than they would otherwise be, reflecting more incoming solar radiation back to space. Historically, global shipping lanes, concentrated along the North Atlantic routes between Europe and North America, had been producing a continuous supply of these aerosols, creating a slight but measurable brightening of marine clouds along those routes. This brightening effect had, in essence, been inadvertently geoengineering a modest cooling of the ocean beneath the shipping lanes. When the regulations took effect in 2020 and sulfur emissions dropped by 80%, that inadvertent cooling was removed. The North Atlantic, stripped of the aerosol cooling that had been masking some of the greenhouse gas-driven warming, began expressing the underlying warming signal more directly. Papers in Earth's Future from Jordan and Henry in 2024 estimated that the IMO 2020 regulations had accelerated global warming by approximately 2 to 3 years. Separate analysis by Gettleman and colleagues in Geophysical Research Letters found that the regulations had produced approximately 0.12 watts per square meter of additional radiative forcing through cloud changes. These are not dramatic numbers in isolation. Applied to an ocean that was already being heated by record greenhouse gas concentrations, atop a multi-decade warming trend, they were, in the language of climate scientists, a meaningful additional forcing. The Communications Earth and Environment paper by Gonaldo and colleagues describes the 2023 event as internal variability effect doped by climate change. The word doped is deliberate. Natural variability, the kind of atmospheric circulation anomaly that produced the anomalously weak winds, is always present. What climate change has done is raise the baseline from which that variability departs. A weak wind summer in the 1980s produced a warm North Atlantic. The same weak wind summer in 2023, atop a warmer ocean, with less aerosol cooling from shipping, produced the most anomalous ocean warming event in the measurement record. One of the most important and most underreported aspects of the North Atlantic marine heat wave is that the conditions that drove it have not fully resolved. The Nature paper by England and colleagues, published in June 2025, is explicit about this. The anomalous warming of the surface mixed layer formed a near basin-wide anomaly that had persisted over much of the North Atlantic basin through the end of the study period. The Yale Climate Connections analysis from May 2026 documented that sea surface temperatures in the Gulf of Mexico as of May 11, 2026, were tied with May 11, 2024, as the warmest on record for that date. Ocean heat content in the Gulf, a measure that integrates warming through the full mixed layer rather than just the surface, remained near record levels. The persistence of ocean heat anomalies is governed by ocean physics that operate on different timescales than the atmosphere. Once the ocean surface mixed layer warms significantly, some fraction of that heat is transferred downward into the seasonal thermocline and beyond, where it is sequestered from direct atmospheric exchange for months or years. Some fraction stays near the surface and can be remobilized rapidly by subsequent atmospheric forcing. The ratio between these depends on the mixing dynamics of the specific region, the depth of the mixed layer, and the subsequent wind patterns. What this means practically is that the 2023 anomaly did not end when the news cycle moved on. It deposited thermal energy into the North Atlantic's upper ocean that continues to influence the surface temperature and ocean heat content of the basin, and to influence everything those things drive. The rate at which the ocean can export excess heat downward depends in part on the mixing depth, which is determined by subsequent wind strength and by the stratification the warming itself creates. Here is the compounding mechanism. A warm, shallow mixed layer is more stratified than a cool, deep one. The density contrast between the warm surface and the cooler water below is greater. More stratification means less mixing. Less mixing means the heat stays near the surface longer, continued solar absorption adds to it, and the excess heat persists even if the atmospheric forcing that created it has moved on. The anomaly partially maintains itself by creating the conditions for its own continuation. This self-reinforcing mechanism was one factor that led England and colleagues in their Nature paper to emphasize the potential implications of the 2023 warming for the Atlantic meridional overturning circulation. Because a persistently warm, stratified North Atlantic surface is exactly the kind of perturbation that could affect the density-driven sinking that powers the AMOC. The 2023 anomaly may not be a temporary episode. It may be a step change that has reconfigured the baseline thermal state of the North Atlantic's upper ocean. There is a secondary reinforcing mechanism that the England et al. Research team identified: the proximity of the 2023 heating to Greenland and to the source waters for the Atlantic meridional overturning circulation. The AMOC, the large-scale ocean circulation system that transports warm water northward in the Atlantic and cold water southward, acting as a planetary heat distribution system. Anomalous warming in the source regions for the AMOC's deep water formation, the subpolar North Atlantic, has potential implications for the AMOC's future behavior that the research community is still working to quantify. But the directional signal from the available research is consistent. Sustained anomalous warming in the North Atlantic subpolar regions is the kind of perturbation that can affect the AMOC stability on multi-decadal timescales. And an AMOC that weakens substantially would produce downstream climate consequences across the entire North Atlantic basin and beyond. That is a long timescale story for a different investigation. The near-term story, the consequences of sustained record-level ocean heat in the North Atlantic for the ecosystems and atmospheric systems that depend on normal ocean temperatures, is what this investigation is focused on. And those consequences are not hypothetical. They are measurable, documented, and ongoing. In mid-July of 2023, something happened in the Florida Keys that the scientific monitoring infrastructure had been dreading for years and had hoped to avoid for at least another decade. The water temperature at NOAA's coral reef monitoring stations crossed the local bleaching threshold, 30.63 degrees Celsius, on June 14, 2023. That was the earliest bleaching threshold crossing in the satellite measurement record, which extends back to 1985. Derek Manzello, the coordinator of NOAA's Coral Reef Watch program, described the timing as starting a full 5 to 6 weeks earlier than the previous 8 mass bleaching events recorded in the Florida Keys since 1987. On July 13th, the water temperature at the satellite monitoring station reached 33.6 degrees Celsius, 92.5 degrees Fahrenheit. The bleaching alert reached level 2, the highest level in NOAA's warning system, indicating accumulated heat stress sufficient to cause widespread coral mortality on July 16th. It remained at level 2 through September 30th. Coral bleaching occurs when water temperatures rise above the local maximum that corals have adapted to by approximately 1 degree Celsius for extended periods. The mechanism is specific. Corals live in symbiosis with microscopic algae called zooxanthellae, which reside in the coral's tissues and provide up to 90% of the coral's energy through photosynthesis. When water temperatures exceed the coral's thermal tolerance, the zooxanthellae produce reactive oxygen species, chemical stress signals, and the coral expels them. Without their algal partners, corals become white, bleached, and begin to starve. If temperatures return to normal quickly enough, corals can reacquire zooxanthellae and recover. If temperatures remain elevated for weeks, the corals die. The 2023 event in the Florida Keys was not bleaching in the conventional sense of a stressful but survivable experience. At some locations, Horseshoe Reef and Chica Rocks in the Keys, satellite remote sensing and in-water surveys documented conditions that exceeded anything in the observational record. Ocean temperatures at some reef sites exceeded 38 degrees Celsius, 100 degrees Fahrenheit. The peer-reviewed study analyzing this data, published in 2025, noted that coral mortalities at some sites were complete, not 90%, complete. The fourth global coral bleaching event, confirmed by NOAA in April 2024 and covering the period from February 2023 through at least April 2024, affected at least 53 countries, territories, and local economies. Derek Manzello, reporting on the scale, stated that 98.5% of reef areas in the Atlantic Ocean experienced bleaching level heat stress during that period. Globally, approximately 54% of reef areas experience bleaching level heat stress, approaching the record of 56.1% set during the 2014 to 2017 global bleaching disaster. The Wikipedia documentation of the 2023 to 2025 global bleaching event notes coral mortalities reaching up to 93% in some areas along the Pacific coast near Mexico. The Florida Keys Reef, the only living barrier reef in the continental United States, a system that took thousands of years to construct and that supports a marine economy generating billions of dollars annually in dive tourism, recreational fishing, and commercial fisheries, had already lost roughly 40% of its coral cover over the past 4 decades before 2023. The 2023 event imposed heat stress that those already depleted reefs had no reserve capacity to absorb. The recovery trajectory from a bleaching event that reached level 2 heat stress for 3.5 months following decades of prior stress is measured in decades at best. For some species, recovery may not occur before the next bleaching event arrives. The projection published in Rapid Recent Warming of Coral Reefs in the Florida Keys before 2023 had estimated that annual bleaching, Conditions severe enough to stress corals every year with no recovery interval would occur at Florida Keys reef sites between 2027 and 2035, depending on the specific site. 2023 demonstrated that the projection had underestimated the pace of change. The event that was expected in a decade arrived a decade early. The coral bleaching event has a visual signature: white reefs, documented by divers and satellite sensors, covered in news stories and social media. It is the face of what is happening to the North Atlantic marine ecosystem. What is happening beneath that visible signal in the invisible lower layers of the ocean food web may ultimately be more consequential, and it is receiving far less attention. Phytoplankton, microscopic photosynthetic organisms that drift in the ocean's sunlit upper layers, are the foundation of virtually every marine food chain. They are the base that everything else rests on. Zooplankton eat phytoplankton, forage fish eat zooplankton, larger fish eat forage fish, apex predators eat larger fish. Remove or diminish the foundation, and the entire structure above it destabilizes. Phytoplankton also perform a function that extends beyond the food web. They produce roughly half of the Earth's atmospheric oxygen through photosynthesis, and they drive the biological pump that sequesters carbon dioxide from the atmosphere into the deep ocean. Marine heat waves damage phytoplankton through multiple mechanisms. The most direct is thermal stratification. When the ocean's surface warms sharply, as it did in the 2023 North Atlantic event, the temperature difference between the warm surface layer and the cooler water below increases, a phenomenon called increased stratification. Stratification is the enemy of phytoplankton productivity because it prevents the upwelling and mixing that brings nutrients from the nutrient-rich deep water to the nutrient-poor sunlit surface. Phytoplankton require both sunlight and nutrients. The sunlight is abundant at the surface. The nutrients are abundant at depth. Normal ocean circulation, driven by winds and temperature gradients, continuously mixes these layers, sustaining phytoplankton growth. Intense stratification cuts off that circulation, producing a warm, nutrient-depleted surface ocean where phytoplankton starve for nitrogen, phosphorus, and iron, even as they are bathed in sunlight. The Mongabay analysis of the 2023 North Atlantic event, published in October 2023, reported that record North Atlantic heat was contributing to phytoplankton decline across the eastern North Atlantic. Satellite chlorophyll measurements, the standard indicator of phytoplankton biomass, showed declining concentrations in the stratified regions of the warming. The European Space Agency's analysis of marine heat wave impacts on phytoplankton, published through their climate research programs, documented that intense marine heat waves delay the timing of phytoplankton blooms. The critical spring event in which phytoplankton populations explode as light and nutrients align, creating mismatches with the zooplankton that depend on those blooms for reproduction. A November 2025 Mongabay analysis, citing research published in 2025, documented that more than 32% of the global ocean area between low and mid-latitudes was showing significant decreases in chlorophyll concentration. Ocean greenness, over the period from 2001 to 2023. Less than 18% showed significant increases. The authors documented a substantial reduction in the overall frequency of high chlorophyll events, the algal blooms that signal productive ecosystems, across the warming ocean. The ocean is getting less green. The foundation of the food web is shrinking. The cascade from phytoplankton to zooplankton to fish follows with the kind of ecological inevitability that the scientific literature describes as trophic cascades. When phytoplankton decline, either in total biomass or in the shift towards smaller, less nutritious species that warm water favors over the large, lipid-rich species of cold water, zooplankton populations follow. When zooplankton decline, the forage fish that eat them, the herring, the anchovies, the capelin, the sand eels, lose their food supply. When forage fish decline, the commercial fish species that eat them lose theirs, followed by the seabirds, the whales, the dolphins, and every other predator in the system. This is not a projection. The Marine Stewardship Council's analysis of warming seas in the Northeast Atlantic cited research from Dr. Christopher Free at the University of California, Santa Barbara, who documented that the 2011 Western Australia marine heat wave and the 2014 to 2016 U.S. West Coast marine heat wave both reduced fish populations to the point that fisheries closed for more than 3 years to rebuild stocks. The Gulf of Maine northern shrimp fishery, Pandalus borealis, a commercially important cold water species, collapsed following the 2012 Northwest Atlantic marine heat wave. The fishery was closed in late 2013 and has remained closed since. Warm water arrived. The shrimp did not recover.
What the 2023 North Atlantic event set in motion is a version of this cascade scaled to a basin covering millions of square kilometers, involving dozens of species and dozens of commercial fisheries, at a moment when the cold water thermal refuges that these species need are shrinking in all directions simultaneously.
The fish are leaving. Not all of them, and not permanently, but measurably, documentably, and in ways that are reshaping commercial fisheries management across the North Atlantic in real time. Species range shifts in response to ocean warming have been documented across dozens of taxa in the North Atlantic. The mechanism is intuitive. Fish, like all ectotherms, have preferred temperature ranges within which they thrive, and lethal temperature limits at both ends. As ocean warming raises the temperatures in their historical ranges, fish move northward toward cooler waters at higher latitudes, or deeper where temperature gradients still provide the thermal environment they require. The NOAA fisheries analysis of these habitats shifts notes that the center of biomass, the geographic center of gravity of a fish population, has been shifting northward for dozens of North Atlantic species over multi-decade periods. What the 2023 event accelerated is the pace and scale of those shifts. NOAA Fisheries' documentation of marine heatwave impacts on species distributions found that a 2012 marine heatwave in the northwest Atlantic pushed commercial species, including squid and flounder, hundreds of miles northward in a matter of months. The same research noted, modern-day marine heatwaves can induce thermal displacements comparable to those from century-scale warming trends. The scale of thermal displacement that normally accumulates over a century of gradual warming can be imposed on a fish population in a single severe heatwave season. For the North Atlantic, this has produced a management crisis that the Marine Stewardship Council described with unusual directness in its analysis of warming seas. The northward shift of Atlantic pelagic fish species, herring, mackerel, blue whiting, is moving them across international jurisdictional boundaries that were drawn based on historical species distributions. When a fish stock's center of biomass moves from Norwegian waters to Russian waters, or from EU waters to Icelandic waters, the entire framework of international fisheries management, the quotas, the access agreements, the stock assessments, becomes misaligned with where the fish actually are. The MSC's Aaron Priddle stated the problem explicitly. Policymakers must find a way to incorporate stock shift changes into long-term and robust fisheries management plans. Without joined-up and effective planning, our fisheries resources could be put at risk of overexploitation, overfishing, and even stock collapse. The Black Sea bass example, documented by researchers at the University of Florida, illustrates the specific management challenge. Black Sea bass range along the U.S. Atlantic coast and have historically been managed under stock assessment frameworks calibrated to their historical distribution. Over the past decade, commercial landings have more than doubled in the New England and Mid-Atlantic regions as the species has shifted its range northward. The existing management frameworks are not designed to track a species that is actively relocating its center of biomass in real time. Data collection, gear regulations, and quota allocations all assume a relatively stable distribution. When the distribution changes rapidly, as it has under the warming that accelerated in 2023, the management frameworks lag behind the biology. The broader consequence is fishing effort concentrated in areas where stocks are newly arrived and potentially still in transition, while historical grounds are depopulated of the target species. Fishing communities built around specific species in specific locations face a double bind. The fish are moving, but the boats, the gear, the processing infrastructure, and the regulatory licenses are tied to the historical locations. The economic disruption from species range shifts is not measured just in fish caught or not caught. It is measured in fishing communities that cannot follow their quarry because everything that supports their industry, except the fish, is still in the old place. There is one specific North Atlantic fishery situation that the Marine Stewardship Council analysis invoked as an explicit cautionary historical parallel, and it deserves attention because it illustrates what happens when a temperature-driven shift in fish distribution intersects with inadequate management. Atlanto-Scandian herring, the North Sea and Norwegian sea herring stock, was one of the most abundant fish populations in the world through the mid-20th century. It supported enormous commercial fisheries that were central to the economies of Norway, Iceland, the Faroe Islands, and other North Atlantic fishing nations. In the 1960s, a combination of overfishing and a cold water period that contracted the stock's distribution pushed the population into collapse. By the early 1970s, the stock had crashed to such extreme lows that the fishery was effectively closed. It took decades of protected recovery to rebuild the population to something approaching its historical levels. The MSC cited this history specifically in the context of what warming-driven range shifts and management failures could produce again. The conditions in 2023 and the years following are different from the 1960s in the specific mechanism driving the disruption. It is temperature-driven northward shift rather than cold-driven contraction. But the underlying dynamic is similar. The fish are in places the management system was not designed for, at the same time that warming-driven productivity changes in the base of the food web are reducing the carrying capacity of the ecosystem that supports them. What this means practically is that the fish stocks that have shifted northward into historically unmanaged areas may be subject to uncontrolled or poorly controlled fishing effort because the regulatory frameworks for those areas were not written with abundant fish populations in mind. The fish arrive in waters where they were historically rare. Local fishing industries, seeing the new abundance, increase effort. The stock assessments for those waters do not accurately reflect the influx of new animals because the surveys were designed to find fish where fish used to be. A stock that is simultaneously stressed by a warming food web and subject to uncontrolled fishing effort in its new range is in a precarious position. The commercial value at stake is substantial. The North Atlantic supports some of the world's most important commercial fisheries: cod, haddock, halibut, pollock, herring, mackerel, tuna, shrimp, lobster, that collectively provide protein for hundreds of millions of people and economic livelihoods for coastal communities across 12 nations. Climate-related fishery losses globally have already resulted in billions of dollars of lost catch in recent years, according to the EPA's Climate Indicators documentation, directly harming jobs, livelihoods, and local culture. The 2023 event and its ongoing ecological consequences are adding new pressure to a system that was already struggling to reconcile the pace of biological change with the pace of management adaptation. The North Atlantic marine heatwave is not only an ocean story, it is an atmosphere story. And the atmospheric story is where the impacts extend from the coast to the continent, from the fisheries to the weather that falls on inland cities, from the coral reefs to the hurricane tracks that threaten the Gulf Coast. The North Atlantic Ocean is the primary heat and moisture source for European and North American weather systems. The interaction between the ocean and the atmosphere, the continuous exchange of heat and water vapor at the sea surface, drives much of the weather variability experienced across the Northern Hemisphere. When that ocean surface is anomalously warm, it alters the atmospheric circulation that overlies it, changes the moisture supply to the atmosphere, and modifies the temperature gradients that steer weather systems. The effects are not limited to the ocean and its immediate coastal margins. They propagate inland through the jet stream and through changes in blocking patterns, the atmospheric configurations that park weather systems in place for extended periods. The Nature Communications study by Yuan and colleagues, published in July 2025, documented a specific mechanism connecting the 2023 North Atlantic anomaly to the devastating western U.S. heat wave of that summer. The anomalously warm tropical Atlantic enhanced atmospheric convection over the Caribbean Sea, producing an anticyclonic Rossby wave source over the Great Plains, enhancing subsidence and significant surface warming. The North Atlantic heat, in other words, contributed to the atmospheric blocking pattern that produced the longest stretch of record-breaking heat wave in the southwestern United States, affecting over 100 million people, causing over 200 deaths, and generating $14.5 billion in economic loss. The ocean anomaly thousands of miles away was an upstream forcing factor in a North American extreme weather event. This teleconnection, the technical term for atmospheric linkages between remote ocean conditions and distant weather patterns, is not a speculative mechanism. It is a documented feature of how the coupled ocean-atmosphere system works, and it is the reason that oceanographers and meteorologists monitor North Atlantic sea surface temperatures as a predictor of Northern Hemisphere summer weather variability. What is new about the 2023 and subsequent anomaly is the magnitude of the ocean signal being fed into that teleconnection system, a signal so far outside the historical range that its downstream atmospheric consequences are themselves outside the range that historical analogs can be used to predict. There is a specific regional consequence of the North Atlantic warming that European meteorologists and climate scientists have been tracking with significant concern: the influence of warm North Atlantic temperatures on European summer heat waves. The Copernicus analysis from July 2023 documented that as the North Atlantic anomaly developed, warm air masses from the anomalously warm ocean moved toward Europe, contributing to above-average land temperatures across the British Isles, France, and Scandinavia. The study by Berthu and colleagues, cited in the scientific data paper on the 2023 marine heatwave, demonstrated that exceptional atmospheric conditions in June 2023, linked to the North Atlantic warming, generated a northwest European marine heatwave that contributed to breaking land temperature records, not just ocean temperature records. The pathway from warm ocean to warm land is not mysterious. The North Atlantic is the primary moisture and heat source for European weather systems. The temperature of the ocean surface determines how much latent heat is transferred to the atmosphere through evaporation, and how much sensible heat is transferred through direct contact. A warmer ocean delivers more of both, modifying the properties of the air masses that travel eastward toward the European continent. Air masses that have traversed anomalously warm ocean are warmer and moister than they would otherwise be when they arrive over land. And when blocking patterns trap those air masses over the continent during the summer, the result is the compound of anomalously warm ocean and anomalously persistent blocking that characterizes the most extreme European heat events. This ocean-land connection means the North Atlantic thermal anomaly is not only a maritime problem. It is a continental European problem, a British Isles problem, and a Scandinavian problem. The excess heat that entered the North Atlantic in 2023 has been cycling through the climate system. Some of it warming European land surfaces, some of it entering the deep ocean, some of it being exported northward toward Greenland. The fraction that reached land drove heatwave conditions on a continent that, like the Gulf Coast of the United States, built its infrastructure around climate assumptions that the North Atlantic is actively undermining. The modification of trade winds is a second atmospheric consequence of the North Atlantic anomaly with global implications. The trade winds, the easterly winds that blow from the subtropical high-pressure zones toward the equator, are driven by the temperature contrast between the warm tropics and the cooler subtropics and mid-latitudes. When the mid-latitude North Atlantic warms disproportionately, it reduces that temperature contrast in the eastern Atlantic and subtropics, weakening the trade wind system. Weakened trade winds reduce the upwelling of cold, deep water in the eastern tropical Atlantic, the upwelling that normally moderates temperatures in the tropical Atlantic main development region for hurricanes. Less cold water upwelling means warmer tropical Atlantic surface temperatures. Warmer tropical Atlantic surface temperatures mean more energy available for hurricane formation and intensification. This feedback, anomalous North Atlantic warming, weakening trade winds reducing cold water upwelling, reduced upwelling producing warmer tropical waters fueling more intense hurricanes, is the mechanism by which an ocean anomaly in the mid-latitude North Atlantic connects to the hurricane season in the tropical Atlantic. It is not a simple or linear mechanism, and its magnitude varies year to year. But the direction is consistent, and the 2024 hurricane season provided direct evidence of it operating. The 2024 Atlantic hurricane season was not simply active. It was anomalously intense in a specific way that the Geophysical Research Letters study by Harris and colleagues, published in November 2025, analyzed in technical detail. The season saw record-breaking sea surface temperatures in the western tropical Atlantic fuel the development of major landfalling hurricanes when atmospheric conditions aligned with those ocean conditions. Hurricane Beryl, which formed in late June 2024, became the earliest forming Category 5 hurricane on record, powered in large part by sea surface temperatures in the tropical Atlantic that were closer, as NOAAclimate.gov noted, to what would be expected in mid-September at the height of hurricane season. In the following 24 hours after it first formed, Beryl rapidly intensified into a hurricane. 24 hours after that, it underwent another instance of rapid intensification to become a Category 4 hurricane, the first Category 4 hurricane ever recorded in the month of June. The 2024 season, in the words of NASA's Scientific Visualization Studio analysis, was characterized by above-average activity and significant impacts, heavily influenced by unusually warm sea surface temperatures that fueled storm development and intensification. The season was also marked by rapid intensification events, exemplified by Hurricane Milton, which escalated from Category 1 to Category 5 at near-record speed. Climate Central's analysis of the hurricane season documented something that places the 2023 and 2024 ocean anomaly in direct connection to hurricane behavior. Since April 2023, global sea surface temperatures had been continuously hotter than any period on record, and by a wide margin. June 2024 marked 15 consecutive months of record-breaking global sea surface temperatures. Climate Central's Climate Shift Index. Ocean analysis found that human-caused climate change made the warm ocean waters that fueled Hurricane Beryl up to 400 times more likely. In the North Atlantic, the number of storms that quickly intensified from Category 1 or weaker into a major hurricane more than doubled from 2001 to 2020 compared to 1971 to 1990. The connection to the North Atlantic anomaly runs through the specific mechanisms identified in the atmospheric research. The record warm North Atlantic of 2023 deposited heat into the ocean that persisted into 2024. The trade wind weakening associated with the anomalously warm mid-latitude North Atlantic reduced the cold upwelling in the tropical Atlantic that would normally moderate hurricane season sea surface temperatures. The result was a tropical Atlantic that entered the 2024 hurricane season at temperatures closer to September averages than June averages, a months-long head start in the ocean heat accumulation that typically builds through the summer toward peak hurricane season intensity. What the Harris et al. Paper identified as the mechanism behind the 2024 ocean conditions was itself unusual. Warm water was advected to the west by a rarely observed zonal pathway combined with anomalous air-sea heat transfer to produce record-breaking temperatures in the western tropical Atlantic. The confluence of multiple drivers, each unusual in isolation, collectively unprecedented, is the ocean equivalent of the compound event framework that atmospheric scientists use to understand why certain events are so much more extreme than any single forcing factor would predict. Hurricane Lee in 2023 provided a preview of what this environment enables. Lee surged from a tropical storm to Category 5 status in the central Atlantic between September 6th and September 7th, a rate of intensification that prompted some meteorologists to use the term hyper-intensification. Kieran Bhatia, head of climate solutions for the Americas at the reinsurance brokerage Guy Carpenter, noted that Lee's intensification rate placed it in the top 0.04% of all 24-hour intensity changes in the Atlantic, seventh in the satellite era to intensify by 80 miles per hour or more in a single day. The ocean that produced Lee, that produced Beryl, that produced Milton, is not a temporarily warmer ocean that will return to its pre-2023 state. It is an ocean that has absorbed the warming of 2023 and retained it, that has been amplified by years of greenhouse gas forcing, and that will continue to provide the energy budget for Atlantic hurricanes in 2025, 2026, and beyond. And this is where the story takes the turn that most coverage of the North Atlantic warming event has not followed. Because the narrative that most people have encountered, when they have encountered it at all, treats the 2023 North Atlantic anomaly as a discrete event that peaked, generated some alarming headlines, and then receded. The coral bleaching happened, the fish moved, the hurricanes were intense, and then the next news cycle arrived. What the monitoring data actually shows is different. The Yale Climate Connections analysis from May 2026 documented that sea surface temperatures in the Gulf of Mexico as of mid-May 2026 were tied with the same date in 2024 as the warmest on record for that date. Ocean heat content in the Gulf remained near record levels. The North Atlantic warming that began in 2023 has not reverted to a pre-anomaly baseline. It is modulated, higher at some times, lower at others, but the structural background level of ocean heat content has remained substantially elevated compared to the pre-2023 period. The Communications, Earth, and Environment paper by Ginaldo and colleagues makes a specific and important statistical point about this persistence. At the current warmer background climate state, the 2023 event is assessed as a decadal type event when considering the full North Atlantic Ocean. A decadal type event. Not a once in 500 years event from the perspective of the current climate system. From that perspective, something of this magnitude should be expected roughly once per decade going forward. What was previously practically impossible has become merely unusual. What was statistically a once-in-5-century event in the pre-industrial climate system is now a once-in-10-year event in the climate system we are currently building. This is the inflection that the 512-year return period paper in Nature was documenting when it noted that, without a global warming trend, such an event would have been practically impossible. The global warming trend did not merely raise the probability of the 2023 event. It moved the event from outside the range of plausible outcomes into the range of expected decadal variability. The return period is not shrinking gradually. It has already collapsed. And that collapse has occurred while the ecological systems of the North Atlantic, the coral, the phytoplankton, the fish populations, the food webs, were still recovering from the previous acute stressors they had been subjected to. They have not recovered. They will not recover if the next anomalous event arrives before the ecological debt from the 2023 event has been paid down. And the monitoring data suggests that the thermal environment that makes such events possible is not retreating.
That is what the next sections of this investigation examine: what the range of future trajectories actually looks like, what the evidence most strongly supports, and what the honest assessment of this situation demands.
Every marine ecosystem has a reserve capacity, a physiological and ecological buffer that allows it to absorb stress without catastrophic failure. Individual corals can survive a bleaching event if temperatures return to normal before the accumulated heat stress exceeds their tolerance threshold. Fish populations can withstand a bad reproductive year if adult biomass is sufficient to sustain the stock. Phytoplankton communities can recover from a stratification-driven nutrient limitation if the mixing resumes before the larger food web has contracted in response. The problem that the 2023 North Atlantic anomaly has created, and that the persistence of anomalous ocean heat is compounding, is that the reserve capacity across multiple systems was already substantially depleted before 2023 arrived. The Florida Keys Reef had already lost 40% of its coral cover over 40 years. The Florida Keys had already experienced 8 mass bleaching events since 1987, each of which imposed heat stress before the reef had fully recovered from the previous event. The fish populations of the northeastern Atlantic were already adapting to a multi-decade northward shift in thermal habitat. The phytoplankton communities of the subtropical Atlantic were already experiencing the stratification effects of the warming that had been building since the 1980s. The 2023 event arrived into an ecosystem that had already cashed in most of its reserve. The result is not simply a proportionally more severe version of previous acute events. It is a qualitatively different situation, one in which the threshold between stressed but recoverable and collapse beyond recovery has been crossed for some components of the system, and where other components are so close to that threshold that the next acute event may be sufficient to push them over. Coral ecology has a specific concept for the point of no return, the bleaching interval. Corals require time between bleaching events to replenish their zooxanthellae, repair their tissues, and rebuild their energetic reserves. The average bleaching interval across the Great Barrier Reef has compressed from more than 2 decades between severe events before 1990 to approximately 6 years in the 2021st century period, according to analyses by Hughes and colleagues. In the Florida Keys, the interval between the bleaching events of the 2020 teens and 2023 was insufficient for full recovery from the earlier events. When 2023 arrived with heat stress at a magnitude that exceeded any previous event by a substantial margin, it was hitting a reef that had not recovered from its predecessors. There is a specific biological mechanism by which repeated bleaching events produce cumulative, compounding damage beyond what any single event would cause: the loss of coral diversity. Different coral species have different thermal tolerances. In a bleaching event, the least tolerant species die first, the more tolerant species survive but are stressed. In the next event, the pool of surviving coral is already skewed toward the more tolerant species. The natural diversity that once buffered the reef against a wide range of conditions has been partially lost. The reef becomes less diverse with each successive bleaching event, and a less diverse reef is less resilient to subsequent perturbations, whether those are temperature events, disease outbreaks, storm damage, or the acidification that is simultaneously increasing as the ocean absorbs carbon dioxide. The 2023 event hit a reef that had already lost a substantial fraction of its pre-anthropogenic diversity through 8 previous bleaching events and 4 decades of chronic thermal stress. The ecological compounding extends to the fish populations that depend on the reefs. Coral reef ecosystems support approximately 25% of all marine species, despite covering less than 1% of the ocean floor. The productivity they provide is not proportional to their physical area, but to their structural complexity. The 3-dimensional architecture of living coral provides habitat for thousands of species that would have nowhere to live in a flat, dead reef. When coral dies and is not replaced, the reef structure degrades over years to decades through erosion and bioerosion, progressively losing the 3-dimensional architecture that supports reef biodiversity. The fish species that depend on that architecture, not just for habitat, but for feeding, reproduction, and shelter, decline in abundance and eventually disappear from the reef. For the North Atlantic's commercial fish species, the equivalent compounding dynamic involves the combination of thermal stress, habitat displacement, and food web disruption. A species that is simultaneously pushed northward by warming waters, deprived of zooplankton forage by phytoplankton decline in stratified warm water, and subject to fishing pressure in its new range, is facing stressors in every dimension of its ecology simultaneously. The fisheries science literature describes this as a multi-stressor environment, and documents that organisms in multi-stressor environments frequently show nonlinear responses. collapsing at stress levels that each stressor individually would not produce. The commercial fisheries of the North Atlantic represent one of the most economically important and food security critical marine resource systems on Earth. The region supports fisheries that provide protein for hundreds of millions of people across Europe, North America, and beyond. Cod, haddock, halibut, pollock, herring, mackerel, tuna, swordfish, lobster, scallops, shrimp, species that have sustained coastal communities for centuries and that remain central to the food supply and cultural identity of Atlantic-facing nations. They are in a more fragile state than the public conversation typically acknowledges, and the North Atlantic marine heat wave has compounded existing pressures in ways that the most current stock assessments are only beginning to capture. The Gulf of Maine is the clearest domestic example of the intersection between warming-driven ecological disruption and fisheries management challenge. The Gulf of Maine has been warming faster than approximately 99% of the world's ocean regions, a distinction that was documented by NOAA and academic researchers well before 2023, and that the 2023 event intensified. The American lobster fishery in the Gulf of Maine is currently at peak abundance. Lobster are thriving in the warming waters, but that abundance masks a set of cascading vulnerabilities. The warm water that is good for lobster is not good for the cold water fish species that compete with and prey upon lobster at various life stages. The prey fish that lobster larvae depend on in their early life stages are being affected by the same warming. And the northern shrimp population, Pandalus borealis, whose collapse in 2013 after the 2012 marine heat wave has kept that fishery closed for over a decade, illustrates what happens when warm water arrives for one of the Gulf of Maine's cold-adapted species. The herring situation is particularly concerning because herring are a foundational forage species. They connect the phytoplankton and zooplankton of the lower food web to the tuna, striped bass, marine mammals, and seabirds of the upper food web. Atlantic herring in the Gulf of Maine and Georges Bank have been declining for years, a decline that NOAA stock assessments have struggled to fully explain using historical stock recruitment models that do not incorporate the thermal changes in the ecosystem. The 2023 warming, which extended through the primary summer growth season for juvenile herring, imposed additional stress on a population that was already below reference points. The international dimension of the North Atlantic fisheries crisis is illustrated by the ongoing negotiations over highly migratory species like Atlantic bluefin tuna, which have been documented shifting their distributional center northward and eastward in response to warming, moving into waters where different nations hold fishing rights and where international management frameworks were not designed for a species that is relocating its core distribution in real time. The International Commission for the Conservation of Atlantic Tunas, ICCAT, manages Atlantic bluefin tuna under a quota system calibrated to historical stock assessments. When the stock moves, the quotas are negotiated for historical fishing grounds, overestimate the fish available there, and underestimate the fish now concentrated elsewhere. The management system is chasing the fish, with a multi-year lag built into every assessment cycle. The economic consequences of getting this wrong are not abstract. The collapse of the Atlantic cod fishery in the 1990s, driven by overfishing that the management system failed to prevent because stock assessments were inadequate, and political pressure prevented timely quota reductions, eliminated one of the most productive fisheries in human history, and devastated the fishing communities of Atlantic Canada and New England for a generation. Recovery of the Grand Banks cod stock remains incomplete more than 3 decades later. The management challenge facing North Atlantic fisheries today, thermal displacement, food web disruption, compounding stress, and management frameworks designed for historical conditions, bears structural similarities to the pre-collapse cod situation, with the added complication that this time the driver is ocean warming that cannot be addressed by fishing effort reduction alone. This investigation has been tracking a story that, because of its scale and its implications, attracts a specific set of simplifications, both in the direction of dismissal and in the direction of overclaim. Both deserve direct, honest engagement. The dismissal argument runs roughly as follows. Ocean temperatures are always variable, marine heat waves have always occurred, and the scientific community has a tendency to frame natural variability as exceptional because of confirmation bias toward climate change narratives. The 2023 event was unusual, this argument goes, but it was a product of El Niño, a natural Pacific Ocean phenomenon, combined with ordinary weather pattern variability. The ocean will cool, the corals will recover, the fish will return. The alarmist framing serves scientific and policy agendas more than it serves scientific truth. This argument can be engaged with specific numbers. The El Niño of 2023 was a contributing factor to the global ocean temperature anomaly. The Nature paper that calculated the 1 in 512-year return period explicitly noted that all 11 instances of similar record-shattering SST jumps in climate model simulations coincided with El Niño events. El Niño does contribute, but the North Atlantic anomaly of 2023 was substantially more extreme than El Niño alone predicts. The North Atlantic SSTs surpassed their previous record by 0.42 degrees Celsius, a margin 0.17 degrees larger than the global SST record-breaking margin. El Niño does not primarily drive North Atlantic temperatures. The excess North Atlantic warming had to come from elsewhere, from the shoaling mixed layer driven by anomalous atmospheric circulation, from the removal of aerosol cooling following the IMO 2020 shipping regulations, from the decades of greenhouse gas-driven ocean warming that raised the baseline. The Communications Earth and Environment analysis is explicit. The 2023 event would have been impossible in intensity without anthropogenically driven climate change. Not less likely. Impossible. The coral recovery argument is similarly testable against observations. NOAA's post-2023 monitoring data documents complete die-offs at some reef sites. Dead coral does not recover on the timescale of the next annual warming season. The reef structure erodes over years. The species that depended on the structural complexity of live coral relocate or decline as the architecture degrades. The recovery of a severely bleached coral reef, not to its pre-bleaching state, but to a functional state that supports commercial and recreational fish populations, takes decades under ideal conditions. The 2023 event did not allow ideal conditions. It imposed record heat stress starting 5 to 6 weeks earlier than any previous event on reefs that had not recovered from their 8 previous bleaching events and maintained that stress through September. The overclaim argument runs in the opposite direction. The ocean is collapsing, coral is essentially extinct, the food web has irreversibly failed, and we are approaching an uninhabitable planet within years. This framing deserves equal directness. The North Atlantic food web has not collapsed. Coral reefs have not gone extinct. Many fish populations are declining but have not crossed the threshold of functional collapse. The monitoring data is alarming, the trajectory is deeply concerning, the compounding of ecological debt is real and documented. But the honest assessment of where these systems are requires distinguishing between serious damage and irreversible collapse, because the policy responses and the hope they depend on are different for each. What the evidence supports is the middle position: serious, documented, compounding harm that has crossed threshold into irreversible damage for some components of the system, particularly some coral communities in the Florida Keys and some cold water fish populations in the Gulf of Maine, while other components remain above their critical thresholds but are approaching them in a direction that the current trajectory will reach within years to decades. The distinction between serious and worsening and already collapsed is not a distinction between alarming and not alarming. It is a distinction between a situation that demands urgent response and one that no longer can benefit from it. There is one dimension of the North Atlantic marine heatwave story that has received significant attention in the climate science literature, but almost no sustained coverage in the public sphere, and it may be the most consequential long-term consequence of the anomaly. The Atlantic Meridional Overturning Circulation, the AMOC, is the large-scale ocean circulation system that functions as a planetary heat distribution mechanism. Warm, salty water at the surface of the tropical and subtropical Atlantic flows northward, releasing heat to the atmosphere and warming the climate of northwestern Europe by several degrees Celsius, compared to what latitude alone would produce. As it travels north, this water cools, becomes denser, and sinks in the subpolar North Atlantic, particularly in the Nordic Seas and the Labrador Sea. That sinking drives a return flow of cold water southward at depth, completing the circulation loop. The system operates like a conveyor belt, continuously transporting heat from the tropics northward and redistributing it to the atmosphere. The AMOC has been slowing. Multiple proxy reconstructions of AMOC strength over the past millennium, using ocean sediment cores, ocean isotopes, and direct measurements from the Rapid Monitoring Array deployed across the Atlantic at 26 degrees Greaves north latitude, converge on the conclusion that the AMOC is currently weaker than at any point in the past 1,000 years. The slowdown has been attributed to the freshening of the North Atlantic, reduced salinity driven by accelerated melting of the Greenland ice sheet, and increased Arctic precipitation, which reduces the density of the surface water and its tendency to sink, weakening the circulation. What connects this to the 2023 anomaly is the location of the anomalous warming. England and colleagues' Nature paper specifically flagged the concern. The proximity of the 2023 heating to Greenland and to the source waters for the AMOC's deep water formation has potential major implications for future climate at regional to global scales. Anomalous warming in the subpolar North Atlantic, the precise region that experienced some of the most dramatic temperature departures during the 2023 event, is anomalous warming in the regions where AMOC deep water formation occurs. Warmer surface water is less dense, less prone to sinking, and therefore less capable of driving the overturning circulation. A significant weakening of the AMOC would produce climate consequences that extend far beyond the North Atlantic. Northwestern Europe would experience cooling, the loss of the oceanic heat transport that currently keeps its climate milder than its latitude would suggest. The tropical Atlantic main development region for hurricanes would warm further as the northward heat transport that removes some tropical heat weakens. Global sea level would rise on the U.S. East Coast as the ocean circulation that currently pushes water away from the coast diminishes. Rainfall patterns in the Sahel, the Amazon, the Indian monsoon system all would be affected by changes in the AMOC that alter the global distribution of ocean heat transport. The research community does not have consensus on whether a rapid AMOC collapse, what is sometimes called an AMOC tipping point, is imminent, possible in this century, or more distant. The Communications Earth and Environment paper on North Atlantic warming explicitly addresses the Atlantic multi-decadal variability, which has historically been linked to multi-decadal fluctuations in the AMOC, and suggests that the recent pattern of North Atlantic warming represents a shift from the historical understanding of that variability.
What is clear is that the 2023 North Atlantic anomaly warmed the precise region where the AMOC's deep water formation depends on cold, dense surface water to drive the sinking that powers the overturning. The degree to which this warming influenced the AMOC's near-term behavior and what that influence portends for decades to come is the subject of ongoing monitoring and research. The Rapid Array and its successor measurement systems will provide the most direct observational evidence. What those measurements show in the years following the 2023 anomaly is one of the most closely watched datasets in climate science.
The honest assessment of where the North Atlantic marine heat wave and its consequences are heading requires presenting three interpretations of the trajectory, each consistent with subsets of the available evidence, each carrying different implications for what comes next. Interpretation 1, the favorable case. The 2023 North Atlantic anomaly, while genuinely unprecedented and genuinely damaging, represents the upper end of natural variability in a warming climate rather than a step change to a persistently hotter ocean regime. The atmospheric circulation patterns that produced the anomalously weak winds and the associated mixed-layer shoaling were unusual and are unlikely to recur with the same intensity in consecutive years. The ocean heat content will modulate toward lower levels as normal mixing dynamics resume, and the excess surface heat is distributed downward into the deeper ocean and ultimately dissipated. The coral communities that survived, the majority of Florida Keys reef corals, which bleached severely but did not completely die, will have the thermal stress period of 2024 and subsequent years to partially recover if temperatures moderate. Fish populations will adapt through range shifts, and management frameworks will adjust, slowly and imperfectly, but enough to prevent the acute collapse scenarios. The 2024 and 2025 hurricane seasons, while active, will prove to be elevated but not categorically outside the range that existing infrastructure and warning systems can manage. Under this interpretation, the 2023 event is a severe episode in a worsening trend, alarming and costly, but not the inflection point into a qualitatively different ecological regime. This interpretation has some supporting evidence. The 2024 North Atlantic anomaly, while still elevated, was not as extreme as 2023 in some regional metrics. Some coral that bleached in 2023 has shown partial recovery in subsequent monitoring surveys. Fish populations are resilient systems with multiple mechanisms for adaptation, and the collapse timescale for most North Atlantic commercial stocks, without additional acute stressors, is measured in years to decades rather than months. Interpretation 2, the middle case. The 2023 event represents the first clear signal of a structural shift in the North Atlantic's thermal regime, a shift enabled by the combination of decades of greenhouse gas-driven ocean warming, the removal of aerosol cooling from shipping regulations, and the specific atmospheric dynamics of 2023. That has moved the baseline ocean heat content to a level from which the extremes that were previously once-in-decades events now occur once in years or multiple times per decade. The coral communities of the Florida Keys and Caribbean are now effectively in a permanent state of chronic thermal stress, with bleaching conditions recurring before meaningful recovery is possible. The commercial fish species that supported New England and European coastal economies for centuries are now permanently displaced, northward for much of their historical range, creating a management challenge that the existing international fisheries governance frameworks cannot adequately address. The hurricane seasons of 2024 and subsequent years are systematically more dangerous than historical baselines predicted, and the communities whose emergency planning was calibrated to those historical baselines are systematically underprepared. This interpretation implies damage that is severe, ongoing, and worsening, but that has not yet crossed into irreversible collapse for most North Atlantic ecosystems. The evidence most strongly supports some version of interpretation 2. The statistical analysis in Communications Earth and Environment, that the 2023 event is now a decadal type event in the current climate system, is the clearest quantitative statement of what this shift means. The persistence of elevated ocean heat content through 2024 and into 2026 is the observational confirmation of that assessment. The coral recovery data, limited and showing stress responses in 2024 that began earlier than in 2023, is consistent with a system that does not have the recovery intervals it needs. Interpretation 3, the severe case. The 2023 event and the elevated ocean heat that has persisted since represent the early indicators of multiple ecological tipping points being approached simultaneously, thresholds at which gradual recovery becomes impossible and systems reorganize into qualitatively different states. Coral reef ecosystems in the Florida Keys and much of the tropical Atlantic are crossing or have crossed the threshold at which annual bleaching events prevent the recovery needed to maintain the reef structure that supports dependent species, initiating a trajectory toward functional loss of reef habitat over the coming decades. The phytoplankton declines in the stratified, warming North Atlantic main development region are triggering food web disruptions that will cascade upward through zooplankton and forage fish to commercial species in ways that existing fisheries assessments have not captured. The AMOC is being perturbed by anomalous warming in its deep water formation regions in ways that compound the existing freshwater-driven weakening, advancing the timeline for a significant circulation slowdown that would alter the climate of the entire North Atlantic basin. Under this interpretation, the 2023 event is not merely an episode in a worsening trend. It is the period during which multiple systems crossed from stressed but recoverable to degrading toward collapse. This interpretation is supported by the threshold crossing evidence in the Florida Keys coral data. The complete die-offs at some reef sites represent a genuinely irreversible outcome for those specific coral colonies. It is supported by the Gulf of Maine shrimp fishery data, where the stock that collapsed in 2013 has not recovered in over a decade despite fishery closure. It is consistent with the AMOC monitoring data showing continued weakening. Whether these threshold crossings are localized harbingers of broader system-level tipping points or isolated acute damages within systems that retain overall resilience depends on factors that the current monitoring data cannot definitively resolve. Let's be precise about what the monitoring data, the peer-reviewed literature, and the long-term ecological records together establish as fact versus what remains genuinely uncertain. What is established? Global sea surface temperatures remained at record levels for more than a year from April 2023 onward, exceeding the previous record in 2015 to 2016 by 0.25 degrees Celsius. The North Atlantic exceeded its previous record by 0.42 degrees. Under the current warming trend, a record-shattering jump of this magnitude has a return period of approximately 1 in 512 years. Without human-caused warming, it would have been practically impossible. The 2023 event was primarily driven by anomalously weak winds producing extremely shallow mixed layers, amplified by reduced aerosol cooling from shipping regulation changes and the elevated warming background from greenhouse gases. What is established? The 2023 North Atlantic marine heat wave was unprecedented in both spatial scale and magnitude over the satellite measurement era, forming a near basin-wide anomaly that persisted well into 2024. Ocean heat content in the Gulf of Mexico remained at near record levels through mid-2026. The atmospheric warming associated with IMO 2020 shipping regulations had accelerated global warming by approximately 2 to 3 years, according to climate model simulations. What is established? The 2023 bleaching event in the Florida Keys and Caribbean began 5 to 6 weeks earlier than any previous event, reached level 2 heat stress status, and persisted through September 30th, 2023. Some reef sites experienced complete coral die-offs at ocean temperatures exceeding 38 degrees Celsius. 98.5% of Atlantic reef areas experienced bleaching level heat stress between February 2023 and April 2024. NOAA declared a fourth global coral bleaching event in April 2024, covering at least 53 countries, territories, and local economies. What is established? Record warm North Atlantic sea surface temperatures fueled rapid intensification of Atlantic hurricanes in 2023 and 2024, producing an unusually high proportion of rapidly intensifying storms, including Hurricane Lee's hyperintensification in 2023 and Hurricane Beryl's record-breaking June 2024 formation as a Category 5 system. The number of storms that quickly intensified from Category 1 or weaker into a major hurricane more than doubled in the 20-year period ending 2020 compared to the prior 20 years. What is not established: whether the anomalous ocean heat conditions will persist at current levels, worsen, or moderate over the coming years. The atmospheric circulation patterns that produced the 2023 mixed layer shoaling are inherently variable, and a return to stronger wind regimes would deepen the mixed layer and moderate surface temperatures. The degree to which the 2023 event has perturbed the AMOC in ways that will produce lasting circulation changes remains an open scientific question. The timeline for functional coral reef loss versus slow partial recovery depends on the temperature trajectory over the coming decade, which is not predictable with current models at the precision the question demands. There is a direct question embedded in the title of this investigation that deserves a direct answer. Why, in fact, is a story of this magnitude? An ocean anomaly that peer-reviewed Nature describes as a 1,512-year statistical event that has visibly collapsed coral reefs, disrupted fish populations, fueled hurricane intensification, and potentially perturbed the planet's primary ocean circulation system, not receiving proportionate public attention. The answer has several components, none of them reassuring. The first is spatial. The North Atlantic marine heat wave is an ocean story, and the ocean is not visible from most places where most people live. The closest most people get to the evidence is a summer with unusual jellyfish, or warmer beach water, or fewer fish than expected. These observations are real, but they are not obviously connected to the basin-scale anomaly that caused them. The dead coral is visible only to divers. The declining phytoplankton is invisible to anyone without satellite chlorophyll data. The northward shifted fish are absent from waters where fishermen used to find them, a presence of absence signal that is psychologically difficult to attribute to a cause rather than to bad luck or poor technique. The second is temporal. The consequences of a marine heat wave unfold over years to decades, not days to weeks. The coral that died in 2023 will still be slowly eroding in 2030. The fish populations that lost forage base in 2023 will not show the full downstream consequences in commercial catch statistics until 2025 or 2026, by which time the connection to the original event has been obscured by the complexity of the system. The media and public attention cycle that generates sustained engagement with stories requires immediate, visible, attributable harm, the kind that a hurricane or a wildfire provides in abundance. A marine heat wave provides diffuse, delayed, distributed harm that is no less severe but is structurally resistant to the attention economy's requirements. The third is complexity. Understanding why the North Atlantic warmed so dramatically in 2023, the shoaling mixed layer, the reduced aerosol forcing from shipping regulations, the background greenhouse gas warming, the El Niño contribution, requires holding multiple interacting systems in mind simultaneously. The connection from ocean warming to hurricane intensification to coral bleaching to fisheries management to AMOC behavior is not a simple story with a simple villain. It is a compound story requiring compound analysis. In a public information environment that routinely struggles to sustain attention through second-order effects, this complexity is a structural barrier to engagement. And the fourth is investment. The monitoring systems that track ocean heat content, phytoplankton biomass, coral bleaching, and AMOC strength. The Argo Float Network, the Rapid Monitoring Array, NOAA's Coral Reef Watch, the satellite chlorophyll sensors, are products of decades of scientific investment in exactly the kind of sustained, difficult-to-make interesting ocean monitoring that does not produce dramatic news footage. The sensors that are recording the collapse of the Florida Keys Reef were deployed by NOAA scientists, whose budgets are determined by a political process that has, in various periods of the recent past, treated ocean science as a lower priority than other uses of federal resources. The answer to why is no one talking about it is not that the information does not exist or that scientists are not sounding alarms. It is that the story requires the kind of sustained, technically specific, consequence-focused communication that journalism rarely allocates the resources to sustain, and that the public's existing frameworks for understanding ocean science, clean water, beach closures, oil spills, do not easily accommodate the planetary-scale thermal anomaly the monitoring data is describing. There is also an attribution problem that cuts in an unusual direction. Most large-scale environmental events become comprehensible to the public through a simple causal chain. This hurricane caused this flood, this wildfire burned this town. The North Atlantic marine heat wave does not offer that direct causal chain to most audiences. It contributed to the conditions that fueled Hurricane Lee's hyper-intensification in September 2023. It imposed the heat stress that killed coral at Horseshoe Reef in July 2023. It set in motion the phytoplankton stratification that will reduce zooplankton and forage fish in ways that will show up in commercial catch statistics in 2025 or 2026. Each of these consequences is real. But the connection between the ocean anomaly and any specific consequence is mediated through complex physical, ecological, and economic systems that add layers between cause and effect that most communication frameworks cannot sustain without losing their audience. The final element is perhaps the most structurally challenging. The 512-year return period is a number about rarity. It is the kind of number that should produce shock, the recognition that something has happened, that the historical envelope of natural variability cannot explain, that belongs to a different category of event than anything for which the infrastructure of ocean science, fisheries management, or coastal planning was designed. But the human cognitive response to large numbers of this type tends toward normalization rather than alarm. A 512-year event happened? That seems like a long time. Things that happen once in 500 years are not things I have a mental model for. The number is too large to be viscerally threatening, unlike a Category 5 hurricane forecast, where the categorical system provides immediate, actionable meaning. That cognitive gap between the magnitude of what the statistics describe and the human ability to internalize it as a basis for urgent concern is the last frontier of this story's communication challenge. Signal Watch does not have a solution to that gap that other communication venues have not tried. What we have is a commitment to staying with the evidence wherever it leads and describing it as precisely as the data permits, for as long as the story requires. This story requires years. This investigation will not conclude when the current ocean temperature anomaly eventually moderates. The North Atlantic marine heat wave is not a discrete event with a beginning and an end. It is an episodic expression of a secular trend, a trend that has been accelerating for decades, and that has now crossed into a range where the statistical improbability of extreme events has collapsed from once per civilization to once per decade. The metrics that matter going forward are specific and publicly available. NOAA's Coral Reef Watch, the satellite-based coral bleaching monitoring system coordinated by Derek Manzello's team, provides near real-time updates on bleaching watch warning and alert conditions at reef sites globally. The degree heating week accumulation at Florida Keys monitoring stations is the most direct quantitative measure of the heat stress being imposed on the remaining coral. When that number begins accumulating in June rather than July or August, as it did in 2023, it signals an earlier and potentially longer stress period than corals experienced in previous events. The Argo Float Network, a global array of approximately 4,000 profiling floats that continuously measure ocean temperature and salinity from the surface to 2,000 meters depth, provides the subsurface ocean heat content data that is more predictive of hurricane intensification potential than sea surface temperature alone. The vertical temperature profiles from Argo floats along the main development region tracks of Atlantic hurricanes will show in real time whether the ocean heat content that powered the 2024 season has persisted or moderated through the 2025 and 2026 seasons. The Rapid Monitoring Array, the moored sensor system crossing the Atlantic at 26 degrees north latitude, provides the most direct continuous measurement of AMOC strength available. Its data releases, published by the National Oceanography Center in Southampton, are the primary observational window into whether the AMOC is continuing to weaken, stabilizing, or showing signs of recovery. Changes in the rapid array data are the earliest warning system for the most consequential potential consequence of the North Atlantic anomaly. The USDA's Agricultural Marketing Service and NOAA Fisheries Stock Assessment reports provide the fisheries data, commercial landings, stock assessment updates, range shift documentation that translate ocean ecological change into economic and food security impact. Fisheries management bodies, including ICCAT, ICES, and NOAA Fisheries, will be issuing stock assessments and quota recommendations for the coming years that reflect, or fail to reflect, the cumulative ecological impact of the 2023 warming event. All of it is being watched. The anomaly that peer-reviewed science describes as statistically impossible without human-caused warming is the ocean expressing the consequence of decades of decisions about energy systems, industrial policy, and global emission trajectories. It is not finished expressing those consequences. The heat that is already in the ocean, deposited in 2023 and retained in the years since, is not going anywhere quickly. The ecological debt it created will be paid by the species, the fishermen, and the coastal communities, whose lives and livelihoods depend on a North Atlantic that functions within the range of what the past 10,000 years had made possible. The range has changed, the ocean knows it, the monitoring data shows it, and this channel will keep following it, specifically and honestly, wherever the evidence leads.
We will be here when the next Core Reef Watch bleaching alert goes to level 2. We will be here when the Rapid Array publishes its next assessment of AMOC transport. We will be here when the hurricane seasons of 2025 and 2026 test whether the ocean heat content that fueled Milton and Beryl has moderated or persists. And we will be here when the fisheries data shows whether the North Atlantic ecosystems are stabilizing above their critical thresholds or continuing their descent below them. The ocean is telling us something, 512 years worth of something. We owe it the attention it is demanding.